Okay, hello everyone. Good morning. How are you?
Good morning, Chair.
Okay, good morning.
All right. So hello and good morning. Okay, today the topic to present is carbon-13 NMR spectroscopy done by me, Aina, and Afika. Okay, so this is the learning outcomes. We will be able to analyze a carbon-13 NMR spectrum of a simple molecule to deduce one of the different environments of the carbon atoms present, and second, the possible structures for the molecule. And then the second learning outcome is that we will be able to predict the number of peaks in a carbon-13 NMR spectrum for a given molecule. I hope everyone can actually hear me or not lagging, right?
Yeah, we can hear.
All right, good. Okay, this is the introduction, just a little bit. Unlike IR, the infrared spectroscopy, and mass spectroscopy, a particular NMR spectrum usually gives us a unique molecular structure. There are two common types of NMR spectroscopy that are used to characterize organic structure: the carbon NMR and proton NMR. So it's basically like this. There's a machine NMR that can identify or characterize the organic structure of molecule, and is divided by two. One of it is identify the carbons, and the second is proton, the hydrogen. Okay. So carbon-13. It is the application of nuclear magnetic resonance spectroscopy to carbon. It is similar to proton NMR and allows the identification of carbon atoms in an organic molecule. This carbon-13 NMR relies on the magnetic properties of the carbon-13 isotope. This isotope makes up only about 1% of all naturally occurring carbon atoms, but this is enough for a signal to be detected in an NMR machine. The carbon-13 NMR spectra plot peak intensity versus chemical shift using TMS, which is the tetramethylsilane, as the reference signal at 0 parts per million. So the carbon-13 NMR only detects the carbon-13 isotope. The main carbon isotope, which is the carbon-12, is not detected. That is because carbon-13 has less coupling. Oops, all right. So the solvent used to prepare samples for carbon-13 NMR analysis is the CdCl3. It is a common solvent used for NMR analysis. It is used because most compounds will dissolve in it. It is volatile, low boiling point, and therefore easy to get rid of. It is also non-reactive and will not exchange its deuterium with protons in the molecule being studied. It is also silent in the NMR and will not show peaks to interfere with the analysis of the compound of interest. Like mentioned before, TMS standard is chosen as for the chemical shift. The chemical shift reference standard for carbon-13 is the TMS. Why is this important? Is because first, it's inert. It is non-reactive, therefore it does not interfere with other substances. Due to its volatile property, low boiling point, the NMR samples can be easily recovered. The TMS has a chemical shift at lower resonance frequency. All carbon are equivalent or in the same environment. TMS are relative to most resonance, so it gives just one intense signal. This is just the example how the reading will look like. It will give a sharp peak, a very sharp peak, and then the TMS over there is always represents as 0 ppm. Okay. All right.
Nadira, can you flip
Yes.
your phone to horizontal?
Okay. Wait. I can't.
Better.
Okay.
So next, we are going to learn how to identify carbon environments. As you can see on the next slide, this is an ethane molecule. On the right, you can see there is one peak on the CNMR spectrum. But what does that mean exactly? Well, it means that it has only one carbon environment. So each peak represents a different carbon environment. But how do we identify them? Well, we look at the bonds on each carbon. As you can see on the first carbon from the left, it is bonded to 3 hydrogens and CH3. And then the second one is also bonded with 3 hydrogens and a CH3. So they both have the same carbon environment. Next. So basically, carbon with different bonds will feel the magnetic field differently. Each environment has different chemical shifts, so it appears as a separate peak. Next. So this is a propanol molecule, and you can see there is 2 peaks. Now, again, starting from the first carbon from the left, it is bonded to 3 hydrogens and a COCH3. And the middle one is bonded to an oxygen and 2 CH3s. And then the last one is bonded to 3 hydrogens and a COCH3s. So the first carbon and the last carbon has the same bond, so it is in the same carbon environment. So hence there is 2 peaks. Next. So other than knowing how many peaks there are in a molecule, they will sometimes ask you about the range, which is where the peaks are located in the spectrum. You can find that table, that very pixelated table on your data booklet on page 13. And to make things easier, I zoomed it in the next slide. So for the green carbon, it is a CH, it is bonded to CH2 and then OH. So the range is from 50 to 70. And then the pink one is bonded to CH3. So the chemical range is from 0 to 50. And this is a visual representation of the table to make it easier for you to understand. So each group has different shift range. Now I'm gonna pass it on to Afika, where she will be explaining some more tricky examples.
Okay, Nadira, you can stop the share screen. I'm gonna use mine.
All right.
Okay, so moving on to more examples. So the first examples is 1-methyl ethyl propanoate. As you guys can see, this how the molecules look like. So this the color, this color, different color is represent how many peaks are they in the molecules. So as you can see, has 5 peaks, and we will go through into it. So the first one, which is the farthest one on the right hand side, which is this one. You guys can see.
Yes.
Okay, which is this one, is the methyl group of the left hand side, which attached to the rest of the arching. So basically, it means this carbon. And the chemical shift range is around 14. So it's actually this one. Then the tall peak at around 22, which is the pink one, is due to 2 methyl groups at the right hand at the end of the molecule, which is this carbon. Next is the purple one, which is around 28. And if you look at the table, it could be a carbon attached to a carbon oxygen double bond. So this what it means. The carbon is attached to a carbon oxygen double bond. Hence this one. Before that. Then the color, this carbon, which colored green is which is this peak, I didn't color it, which around 67 is due to different carbon singly bonded to an oxygen. So it refers to this. And as you guys can see at the table, this is the one. And moving on to the peak at 174, just the smallest one, is due to carbon in carbon oxygen double bond in acid or ester. So basically this compound is actually an ester. So you can, as you can see, this the table shows. Another examples is deuterium 2-on, or another name is 3-butene 2-on. So this is how it looks like. So it has 4 peaks. So basically, it means that all the carbon in this molecule are in the different carbon environment. So the first one, which at 26 is a methyl group, which joined to the rest of the molecule by carbon-carbon single bond. So this is the one, carbon-carbon single bond. Next is look at this two peaks, which colored purple. Around this peaks is around 137 and 129. And these are due to carbons at either end of a carbon-carbon double bond. So it refers to this carbon, both carbon double bond. Notice that they aren't exactly in the same environment, and so they don't have the same shift value. So you guys can see that. And the one that closer to the carbon-oxygen double bond has a larger value. So basically, the carbon who is much more closer to the carbon-oxygen double bond has a larger value, which means I'm gonna draw. So basically, this one is referred to this, whereas this one is referred to this. Hence why they have different environment. So the next one, this peak is which under 200 is due to carbon oxygen double bonded. So moving on to drawing compounds from carbon-13 NMR data. So these the examples. Compounds F and G have the molecular formula of this, and both are dinitrobenzene. F has 2 peaks, whereas G has 3 peaks. So I'm gonna give the answer straight away. So this is how it looks like. So why is like that? As you guys can see that F has 2 peaks. So first we have to like make a line of symmetry. It can be either horizontal or vertical. And when you guys like fold it, it must be overlap each other, same. So basically this carbon is the same as this carbon. Whereas this 4 carbon is the same. So hence it has 2 peaks. Whereas the G1, the line of symmetry is actually this. And when you guys fold it, it has like this. This carbon are the same. This one is the same, and these are the same. Hence, it has 3 peaks. Do you guys understand?
3.
Yes.
Okay. So next is passive papers. So basically, most of in the passive paper, most of it they will be asked about how many peaks are there, or sometimes it will combine with hydrogen or proton NMR, and sometimes they also ask about how to draw the isomer of that molecule. So this is one of examples. So this one to state the number of peaks that will be seen on the spectrum of this. So I'm gonna give the answer straight away. So as you guys can see, it has 4 peaks. And if you guys can't visualize it, you guys have to draw it and check whether I have to check like each carbon, whether they have the same carbon environment or different. Then moving on to the part 2 is where there are 2 isomers that have fewer peaks in the carbon the NMR spectrum than the previous one. So they already bolted the fewer. So basically it has to be like fewer than 4 peaks. So it's like 3, 2, or 1 if possible. So the first one is isomer 1. It has 2 peaks. So it has 2 peaks. So look at each of the carbon. This carbon is 1 environment, and these 3 carbons are in the same environment, hence has 2 peaks. Whereas in isomer 2, this carbon is 1. These 2 carbons are in the same environment, and this carbon is another environment. So basically has 3 peaks. Next, also the same. They want to question you guys how many peaks are there. I'm going. So this is the answer. Again, if you guys can't visualize it, you guys have to draw the structure and check whether or not have a line of symmetry, or whether they have the same carbon environment or not. So, okay. So moving on, same. They want to predict number of peaks. So I'm gonna go through. So it has 4 peaks. So since they give this diagram, you guys can easily like draw like can see whether or not how many are they the carbon environment. So I'm gonna draw. So this is the line of symmetry, and as you guys can see that this carbon is 1, and this carbon with this carbon are the same. So it's 1 carbon environment, and this carbon with this are also the same. So hence 1, and this carbon is 1. So basically it has 4 peaks altogether. And for the part 2, they want you to state the chemical shift range of the peaks predicted just now and the number of peaks in each range. So how do we see this? First, we have to see like each of the carbon, as you guys can see that this carbon, the one who attached with oxygen, is actually a carbonyl, which is a ketone. And if you guys see in the data, in the table, in the data booklet, it's the chemical shift range is around 190 to 220, hence this. And next, the carbon, which is bonded as hydrogen to hydrogen net, is alkyl. So the chemical shift range is around 0 to 50 or 20 to 50. And they want to state the number of peaks in each range. So just now, the one carbon that bonded to oxygen have one, so this two, and then this three. So basically they in the same environment carbon atom, but with different shift shift value. So hence in range of 190 to 220 has 3 peaks, whereas this one has 1 peak. So it is like this, something like this in the spectrum. So do you guys understand?
Yes.
Okay, so the next question is how they can distinguish using NMR spectroscopy. So they want to give 2 reasons why TMS is used as standard recording. So just now Nadia say what's the use of the TMS. So this the reason. The first reason is it has one intense peak or OH or OC in the same environment. And the second reason is the volatile or low boiling point, which can be easily removed. Finally, give the structural formula of TMS, like just now. So this structural formula. So that's the end of it. Thank you.
Does anyone have any questions?
So any questions from the floor? From the audience? No questions from the audience. Everyone's so quiet. Are you guys listening to the presentations?
Yes.
Okay, wonderful. So I think that this is really that's really good. Is that okay? We actually is a whole new experience. Okay, using Zoom to present. Okay, it's quite different from our normal presentation. Okay, but of course, aside from that, okay, you don't have audience to look at you, so that is one good thing. So you just have to look at the screen, and of course they have actually managed to see that if you make your screen, so if you're using a phone, if you put it vertical, then the screen will be very small. But if you put it horizontal, then the screen will be bigger. Okay, and then also an audience is going to fill up this form. Okay, so and then the presenter will have to attach your slides over here. So just attach your slides over here, and then so that your friends can check on that. And I'm going to attach the video link later. So it's a very simple one. All right, so your name, your class, then you're going to choose, are you the presenter or the audience? And then after that, what have you learned? For the presenter is what have you learned along the way when you are doing this? And then, and also what do you like about your presentation and any improvement you feel that you need to have?